We continue here talking about circular motion, and the dynamics of circular motion don't really look that much different mathematically from the dynamics of rectilinear motion, but we'll want to make sure that we are really clear about some of the terminology that we use in order to solve problems. Clearly in that video, the ball did slow over time, but for a moment, let's assume it did not. We see the ball traveling in a circle, and let's assume it didn't slow as it went. What direction would you expect to see the net force on the ball as it travels around in a circle? Well, based on the last video, we know that there is a net force pointed toward the center of the circular pan, but what force is actually doing that? There is a contact force acting normal to the surface of the pan, a contact force actually that both the pan and the ball experience, of course, because they are two solid objects not passing through one another. The ball is not sliding across the surface of the pan, it's rolling, so we don't want to talk about it having a sliding friction. If you were to draw a free body diagram of the ball, you would have to point gravity into the screen because this camera angle is looking down at the ball and the pan on the floor. And the bottom of the pan provides a normal force back upward out of the screen toward you. We try not to put ourselves in a position to have to draw vectors that way if we don't have to. So our free body diagram, one of the big tricks to uniform circular motion problems is to draw the free body diagram from a point of view that is not how you would best see the uniform circular motion itself. You want to see the circular motion so that you can see the whole circle, for example, the perspective that we have in this video here. But you want the free body diagram to be drawn as though you are looking tangentially from within the same plane as the circular motion itself. That doesn't really take too much getting used to. A couple examples and you'll feel very comfortable with that. More importantly, with the free body diagram, do I draw this green normal force pointed to the left or to the right? It kind of doesn't matter. You just need to know that the direction that you have it pointed must be toward the center of the circle because you know that that's how the net force points in order for an object to move in a circle. The free body diagram doesn't need to change as the ball moves around in the circle because none of the forces are changing except that the green normal force is changing direction from the perspective of Cartesian coordinates. But in polar coordinates, we know it's always pointed radially inward. The term radial force or centripetal force means that the force is pointed toward the center of the circle. But that term should never appear on your free body diagram. Radial and centripetal are descriptions of the direction of the force. Your free body diagram must give a description of what the force is. In this case, it's a force normal to the side of the pan. Just as you don't call the force of gravitation the down force, directions are not good descriptors and should not be used in free body diagrams. I really like this animation, so I thought I would share this with you, demonstrating how as you increase the number of collisions that the ball makes with the surface, you get to see more and more that the forces are still pointed radially. And so if you have a continuous contact of the ball moving around in a circle, the force that would make it do that is continuously circular. Just sort of to back up our point, I suppose. This is an example of a free body diagram for an object that is traveling in circular motion. It says the car is on level ground, moving away from you and turning to the left. As this car moves, what forces are acting on it? Definitely the force of gravity between the earth and the car, sure. And the force normal between the car and the road, sure. And a force of friction, definitely. If you're having trouble identifying what force is causing the object to change its velocity direction, sketch the problem or look at a given drawing and ask what the different interactions are, and would taking one of them away from the object stop that object from going around in circles? For example, if there was no friction, if this car was driving over ice or mud or muddy ice, it loses friction with the road, and that's when the driver is in danger of not being able to control their turn. So I know friction is my centripetal force, and friction is what goes on the free body diagram. Static friction in particular, because the tire is not sliding sideways. Most problems, it's not that complicated to determine what the force is that is acting centripetally. So we'll make sure we take a look at some that it is a little bit more complicated so that you get some practice doing that. This slide is on here to emphasize that it is often important to observe a turning object from outside that object, in order to properly identify what forces are actually acting. From within a vehicle, as the driver turns the vehicle to the right, you may feel pushed to the left inside the car. But a person outside the vehicle would be more capable of evaluating that you're traveling in a straight line because of inertia and the car turned to the right under you. This is exactly how a centrifuge works, is that the spinning in circular motion causes the test tube to move in a different direction from the instantaneous velocity of its contents, the direction that they are traveling because of their own inertia. So within the reference frame of the test tube, it feels like everything is being pushed toward the end of the tube. We will come back to that in a later video for a cool effect. I guess I just promised that we would circle back to this topic. So a quick summary. An object that is traveling in uniform circular motion is traveling at constant speed. One way that you might be able to determine how fast it's going in terms of meters per second is that an object traveling in uniform circular motion completes one circumference of motion every period of time. So the distance it is traveling is 2 pi times the radius of the circle, and it's doing so in a repeated amount of time that we would refer to as the period. The instantaneous velocity of an object in uniform circular motion at any moment is directed tangentially to the path. The acceleration that it is experiencing is directed radially, and we have two equations that I will provide you for that. The centripetal or radial acceleration is equal to v squared over r, where v is the speed of the object and r is the radius of its circle. That is equal to r omega squared, where r is the radius of the circle and omega is the angular frequency in units of per second. And one of the most important things to know about uniform circular motion, especially in the video that purports to talk about dynamics, is that Newton's second law still applies. It's just that the acceleration is found differently for objects that are traveling in circular motion. But once you have the acceleration, the force acting radially is equal to the mass times the acceleration that is acting radially. Any force that we have talked about to this point in the course can be a centripetal force. Tension, normal force, friction, any of them. And we will do problems in class to make sure it is clear how each of them could do this. So that's the dynamics of uniform circular motion.